Is it working? Great. Okay. Still one student is coming, so. So, are there any questions which I should clarify from last time? No? Or you didn't look for the things? Just, I don't mind, I am paid for teaching, so I am fine. But the thing is that you came to learn something, but that means that you need to read a script or something like that, because the things will start to get complicated and you will lost. Okay, and then it's basically lost of the time for everyone, especially for taxpayers who pays my salary, and you know. So are you reading the script which I am posting on the Moodle? I'm putting some notes there which I am following. I'm trying to explain them. Is someone following them? And also next week, instead of this, you will solve the problems. I posted the homework sheet there. Did someone check what is in the homework sheet? And is it clear what to do? Okay, that's great. So if not, then we will sit here 3 hours or things like that. Just want to tell that. So next week I'm not lecturing. I want to discuss the problems, and you should solve the problems on the Blackboard. So it's good that everyone prepared different problem. You can gather together. I said I will do 1, 2, 3, or we can do together. Does not matter. You can merge and do it together. So 5 people can solve 5 problems. It's important that they are able to present it on the Blackboard. So I want to make it like that, okay? So find your time, go for coffee, discuss the sheet together, make the solutions, okay? Great. So today, it's a chapter 3. And it's a second quantization. Okay, I asked last time, and you said that you heard something about the second quantization, but some people said that I should make it slower or something like that. So that's why I'm doing it slower. Okay? So let's start with paragraph 3.1. And paragraph 3.1 I called like interlude. Why not Schrödinger? And the answer to this question is because this is the main answer. It is impractical. Especially when you are having n large, which means n is the number of particles. And also it's impractical in terms that you are having a system with n particles, you develop the formalism, and now you want to have a formalism for n plus 1 number of particles, or n plus 2 or plus something. The generalization is tedious. Expression gets extremely long. Okay? So this is the main reason. So expressions are too long to take with. Are too long. Okay, so this is the answer by not Schrödinger, and you will see it. I will show one something thing, and then if you would look, even we need to calculate it. We would need to calculate such long expressions. But the way is that if you want to go and do some calculation, you need to keep them with you and bring the big expression with you till the end, and then do some calculations. So the second quantization in that form is more economical. So it's shorter. But of course, when you need to calculate and you unpack everything, you will see it's also getting longer. Okay? So this is, we will not avoid to compute some expressions, but at least to bookkeeping is much simpler. Okay? So this is the main answer why not Schrödinger. So just brief reminder, what is the first quantization? Alex, thank you. Okay, first, that's good. I have it. Thank you. Oh, great. Super. So, yeah, having this. Okay, the first quantization, and I will just explain the logic behind that. Okay. So we are having n particles. And we assume that these particles are distinguishable. Okay, so on the picture this means that, okay, the particles which are distinguishable, okay, and we are having this particle in some system, so we are having n particles, these particles are distinguishable, and we have some system. Which means, for example, particle in the box. Okay. But this means that we know all the eigenstates, single particle. If we take the single particle Hamiltonian, we know all eigenstates of the system. Okay, let's start from fully simple case. So it means that we are having the set of all the wave functions, which I'm writing like that. This is the first wave function, second wave function, etc., 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 and there is the last wave function, which can be in principle infinity. Yeah, but we are having discrete set of wave functions. Okay, so we know that we solve the one particle Schrödinger equation or three particle Schrödinger equation, we are getting the wave functions, and we know that there is a discrete number, which is this energy levels, and assume that this is the eigenstates which we know. Okay. In principle, we don't need eigenstates. We just need a complete set of states which are orthonormal and orthogonal to each other. Okay. But let's assume like that. Okay. And in the first quantization, what we are doing, as I said, so we are having n particles. These n particles are distinguishable. Okay. 1, 2, 3. This is the nth particles. This is 1, 2, 3. This is the n. So we have n particles, so we give them the names. And typical names are 1, 2, 3, n. You can also try the human names. I don't know, Alex, Adam, Eve, I don't know, Eugene. Yeah, so you can imagine many names you can put, but it's very impractical to use the human name. So this is the name of the particles. Okay, so we give them the name, and to describe the system, we just need to say that. To describe the system means we need to tell which particle is in which state. Yeah? So to know the state, we need to know which particle is in which states. For example, the particle number 1 is in the state alpha 27. Yeah, so it's in 27. Particle number 2. Let me use because then I later to you, is in the state alpha 3. Okay, I don't know. And the particle n is also in the state, let's say, alpha 3. Okay. Great. So then the total wave functions. I call it wave functions, but this means the total state. Is basically then we will write it something like that, that it's alpha 27 for this particular case, alpha 3, etc., alpha 3. And there are together n entries. Good. And if I would like to know it in the X representation, this is everything is still abstract, yeah? But if I want to have it in the X representation, okay, or let's call it in the R representation, because in principle R can be like vector, then what we need to do is that we need some wave function psi, which is depending on the positions of those particles, okay? And then it would be something like and I will use And I will use the symbol for these distinguishable particles. I will put here a bracket like this, that they are distinguishable. So later I will also use the sharp angle bracket. But this basically means that the wave function of this particle will be something like that, that it is the alpha 27, for example, at point R1, alpha 3 wave functions evaluated at position 3, up to down, and alpha 3 at point Rn. Clear? What I'm saying is clear? So far, nothing new, right? Great. So in general, instead of this 27 and things like that, I will write it like that, that the first particle is in the state A1, second particle is in the state A2, n particle is in the state An. Okay, here I use the concrete examples, but this can be different number, yeah, and it will change. Good, and then also, if I would like to compute it, then I need to write it in general that here it would be A1, here it would be A2, here it would be An, and all those indices are going over this set, right? So these A1s are these numbers. 1, 2, 3, up to omega. I'm using omega because this index and this index are unfortunately different indices. This labels the position of the particle. This is the name of the particle is hidden here, and this is the index of the state. Okay, just there are two indices, just that you keep that in mind. Okay? Fine, may I go on? Perfect. So there was particles which were indistinguishable. But statistics tell us that in the nature we are having bosons or fermions. And this is the indistinguishable particles. This is indistinguishable particles, and then the wave function for the bosons and fermions should be like that, that if I am changing position of two particles, then the wave function should be either changing or not changing, yeah? So what we know is that for bosons and fermions, the wave function should be fully symmetric, and this should be fully antisymmetric. Which basically just means we need to take these guys and just we need to symmetrize them or anti-symmetrize them. This is the way. So the way you imagine the system that particles are like the way, and you should have in the mind is that you imagine that particles are distinguishable, you give them name, you make something, and then you say, oh, they are not indistinguishable. Okay, so I need to do some symmetrization and anti-symmetrization. Okay? So then let me write it. So, okay, I'm consuming too much space. So if I am then doing it, okay, then let me write it. Then I need to write the wave functions of the bosons or fermions, for example, B or F. I'm just writing bosons or fermions. I have n particles. Then what I need to do is I need to make the symmetrization or anti-symmetrization, which is some constant C, okay? And what you need to do is the summation over the sigma p. I will write it and then explain each point. And this is plus or minus 1 sigma. And then you are having like, either you do it like that, that you keep these indices as fixed, and you are changing the, okay, I will explain it. That's the one way, or the other way, but it's fully equivalent is So what we are hearing is we are changing the arguments. So these things are somehow now changing something, but these things are fixed. So this is fixed. Or the other possibility is opposite, that I will fix those guys and the other will change. So this is the same. And let me explain what is what. Just give me a second. Sigma 1. And what I am now doing is that I am here putting a sigma 1, and I am kicking here R1. And here I am putting alpha a sigma 2. And I am keeping here R2, etc. And there will be a sigma n. And there will be Rn. Good. So in that case, what is changing is here. And what is kept fixed is this one. Okay, so we are not changing these guys. Okay. This constant c, which we will see, or basically it's very quickly to see, the constant c is nothing else as 1 over n factorial. Okay, and now I need to explain what is sigma, or what is p, and what is this plus and minus 1. Okay, so this p, which is brought here, is the group of permutations. So the p is nothing else. It is just the group of permutations. Group of permutations. Of n elements. Okay, so I have 1, 2, 3, etc. to n, and then I'm making some permutations here. So which means I'm, let's say, exchanging 2 and 3, and 1 and, I don't know, 27, and n with something else. So this is the permutations. You know what is it, right? Right? Great. So we are having all together, if I am permuting n elements, then all together I have n factorial permutations. That's the reason why the c is 1 over n factorial. Okay? So p is the group of permutation. Sigma is just sum of the permutation. It's one particular. Okay, but we are summing over all the permutations. So one particular permutation looks like that, as I was telling you. So you take, let's say, 1, 2, 3, 4, 5. Let's assume that n is equal to 5. And one particular permutation is that, let's say, I'm permuting this as 2, 1, what I wrote, 5, 3, and 4. Okay, so I make a one particular permutation. So I change position of that. Then I change the position of this. And then I change the position of this. And it comes of that. Okay, so you just need to count how many times you are permuting. Great. And this plus and minus sigma is basically telling us this is the parity of the permutation. I don't know how to maybe call it. Maybe in some books they put it like absolute value of sigma. Somewhere they write it as a p of sigma. This just want to tell you, I don't know how to write it. So I will just use the sigma. But this means it's a parity of the permutation. So you need to count how many times you change the, you make the swaps. So in particular, in this case, what we are seeing here, the parity of this permutation is what? So how many swaps I need to make to get from this configuration to this configuration? And I see that, okay, here it is one swap because I need to change position of those two guys. And here it is one swap, second swap. Okay, so I need to go once here. I'm exchanging them, and then I need to go also once here, so I'm exchanging them. So I need to make 3 swaps to get from the standard or the canonical position, 1, 2, 3, 4, 5 to the given position. So in that case, this would be 3. Okay? I'm just explaining you. Okay? If I am making even a number of times, yeah, then it will be 4, and what just matters is the parity, whether it's even a number of the swaps or odd number of the swaps, okay? You remember this is just the definition of the determinant in principle, right? So you have exactly the same thing here. Okay, this C, I said it's 1 over n factorial, and okay, And if you are doing that in terms of the wave function, it looks like that. But if you would like to do it in terms of these abstract objects, then I will just write it like that, that if I'm making the permutation, then I will write symbol something like that. Now I wrote it, okay, A1, alpha A2, alpha AN. And if I want to emphasize that is symmetric or anti-symmetric, then I will use these brackets, which exactly just means that I'm making this symmetrization or anti-symmetrization acting on this guy. Okay. Is that clear what I'm doing? This is just nothing serious, but can be a little bit confusing because there are many indices, and once there is such brackets and once there is such brackets. And this operation is basically what I described here. So this is the symmetrization or anti-symmetrization, right? For bosons, we don't care. For bosons, there is a plus sign, but for the fermions, we care there is a minus sign. Can I consider that this is clear? Very good. Then we are going to the next page, and I clean the table. And now we see the operators. So let's now see, if you would like to describe some linear operator, what kind of expression I was telling you we need to keep in mind. Okay, good. So this is just still first quantization. Erase it. Okay, the complication comes if you want to describe the operators, or it's not a complication, like it's a complication. Okay, long expression appears there. So normally we can have some operator T, which is the one body operator, or I can also call it a single particle operator. Normally it would do like that, that you take some quantum mechanical state alpha, and you apply the operator, and normally what it's doing, it's like a matrix, it's mixed the things, so you will get some other state, and the other state is just some over beta, for example, and I will write it the TB alpha. So only to give the operator T, basically what I need to know are those numbers. Okay, so this is just the complex numbers in principle. Great, and if I know them, then I know how the operator T acts on any arbitrary state. So basically T beta alpha is normally something like beta operator T acting on the state alpha. So if I know all those guys for all alpha and beta, I need to pick up some bases. So alpha is coming over my basis of the states, beta is also in my basis of the state. So if I know all the collections of that, I know how every state is working on that, right? Is that clear? So this would be action on the one body operator on one particle. But we are in the situation that we are having more particles. Let us assume they are distinguishable. So now we can ask what is the action of the same operator or the many body state. So now assume that I have my state alpha A1, alpha A2, alpha AN. You see distinguishable, which I can nothing, just imagine that it is alpha A1, alpha A2, like a tensor product of such states, alpha AN. And now I need to describe the action of the operator T on such guy. So if I'm taking such guy, I need to know where this guy is going if I am applying operator T. Okay? The answer is known. We just want to keep that this operator is linear. So we assume that this was the linear operator. So we also want to keep this as a linear operator. And the answer is like that. Okay, by definition, this state okay, so this is just the bracket denoting where it's go. It's basically like that it firstly operates on the state alpha A1, and all others are kept untouched. Then it jumps on the second state. Plus, etc. And last, and then it jumps on this state. Okay, and I'm making a tensor product of the guys. Okay. And now the main point is that, as I said, so we want to know these complex numbers. So if you now ask, what is the matrix elements of this operator in this basis? So basically, you would need the matrix elements of that operator. So what you would need is to know how the matrix elements looks like of such operator, which basically means you need to make something like scalar product T alpha n, okay? And making the scalar product, you know the action, and now you start to see what expression comes out, and the expression will look like that this is like T, B1, A1, and there is a delta function, Kronecker symbol, delta delta 2, delta R2, delta Bn, Rn, plus delta A1, B1, AA1. Okay, here it would be T, B2, A2, etc. Delta Bn, Rn, plus many other terms, and then you would have a term which is like delta B1, A1, delta Bn minus 1, An minus 1, T, Bn, An. Okay. So this is the matrix element of this operator when it acts on the n-particle state. And if you see, this is terribly long expression if you want to work with them. Yeah, if you, okay, you can introduce such symbols, but now assume that you make your theory for the n particles, and now you would like to make it for n plus 1 particles. And then you would like to express the things. Already know these matrix elements, and I would like to know the matrix elements for in this case. And you will see that, okay, you can do it, but the expressions are very horrible in some sense. Yeah, like extension, if you will. Assume I know the matrix elements for how it acts on the n particles. Okay, so it would be such expression. And now I'm asking, okay, knowing this piece of information, how it will look like in that case. And you will get combination of many deltas and things like that. And it's a big sausage which you need to bring with you. So it's not practical. Okay? Anyhow, we need to calculate such matrix elements, and also in the second quantization, it will not bring us anything new. At the end, we will get some long expression or something which we need to calculate effectively, but the bookkeeping is simpler in some sense, okay? So this is one of the advantage of the things. Okay, and this was on the distinguishable particles, and then you can ask me, okay, but you told us about the fermions and bosons, so how it will look like on such state? This is the question now if I'm working on that state. when I made the symmetrization on anti-symmetrization? So the answer is very simple, because this symmetrization and anti-symmetrization is a linear operator. So basically this is the same as to write it like this. P as A acting on alpha A1 alpha AN, like this state. And the thing how it's always understood is that, okay, you change the role of those things. So what you do is you make the symmetrization or anti-symmetrization of those guys. Okay, so this we know. This was defined in the previous steps. So it's some linear superposition of many things. And then we need to make the anti-symmetrization or symmetrization of each of these guys and make the summation of them. Which is even more stupid, because if you really write it in terms of the symmetrization and anti-symmetrization, you will see that you are getting even longer expressions in practice, okay? If you really start to calculate something, you will be very soon starting to use the words like fuck or something like that, because you will see it's too terrible, okay? I'm apologizing that I used that word, but we are coming to fuck space, which is called Fock space. So it was the prelude to that, okay? So it was Fock, not what do you think, okay? Great. So this is the main problem with that. Great. So as I said, we go to Fock space. That's I was really student as you, and I was at one conference, and there was one American talking about the Fock space. And he had so terrible accent that he started, in this Fock space, we have these Fock vectors. And everyone was like, oh, this guy. And then he came and he wrote this, and then we understand he talked about the Fock space. This I consider as a very funny story with my broken English and American accent. Okay, so we are going, so I explained just where is the complication coming. So let's go to the Fock space. Okay, any questions to that? I didn't say anything serious so far, only some notation. Can I go on? Great. So let me erase it. Okay. Fock space. Yeah. Fock was a Russian physicist. And there are some nodes, how he was really calculating, and there are like big nodes, like big piles of paper. He was really doing some calculation of the hydrogen atom, keeping it in the first quantization formalism where all those expression appears, and it was so long. But in museum dedicated to him, there are here notes, and I was saying, wow, that guy was somehow like crazy. He was able to keep it and do this expression and keeping this long expression with him and get the correct result. Okay, so the Fock space, the idea is completely different. So the motivation or the point is like that we are working with indistinguishable particle. So this means that the names does not matter. Names don't matter. Okay, because at the end we are anti-symmetrizing, so who is basically lost at the end, or is washed, and everything is mixed. Okay, so this is the first thing. We really don't need the matter. We don't need to keep the notation about the name, and there is this game changer that. So the new things in this Fock space, this is this game changer, I call it. And the thing is that instead of telling which particle, so I will really write it. So instead of telling which particle is in which state, we take all states and specify and say their occupancies. Okay, so once more, the story before was like that. I will try to draw it. So story before was like that. We take the particles, we give them the names, okay? Then at the end we do the symmetrization, anti-symmetrization. Then we take all states and we put the all states like this. There was the state number 1, state number 2, in principle state number omega, which can be very large number. And we take particle number 1, particle number 2, particle number n. And what we were doing, we were saying that, okay, particle number 1, if you remember, was in the state 27. So there was somewhere alpha 27. Particle number 2 was in the state number 3, okay? And particle n was in the state also alpha 3, and that was the main thing which we had before, okay? That was before. This is this thing. We take the particles, give them the names, and we were saying in which states they are. Okay? So that was like a table. You can imagine that, that we take a table and we said 1 is here, 2 is here. Okay, let's put alpha 3. Make it nicer. Alpha 27. I don't know. Alpha omega. And we were really specifying who is where. So, okay, that was somewhere in 27. 2 was in 3. I don't know, 4, for example, or particle number 3 can be in the state alpha 1. Okay, and the particle number n is also in the state 3. Now we will do the different thing on the picture. Let's do it. Now we do something different. We take all the states, we place them here. Alpha omega. And now we will state how many states are in this state. So now I am putting some counters here. Okay, and I am saying how many states are occupied. So particularly in this case, if I am saying so, state number 1 is occupied once because there was particle number 3 before. Okay, this state is empty, so there is nothing. In the state alpha 3, for example, in this picture I had 2 particles. Does not matter that was the particle number 2 and particle n. We don't care about the name. So there are 2 particles there. Okay, somewhere here was the state alpha 27. And there was a 1 particle, etc. Okay? So by that, I am now encoding the information to something which looks like that. So what I can do is that now I can make a very big vector. I'm putting here the index, I'm putting here the bracket, but here just want to tell that symmetrization and anti-symmetrization is taken care because we are really talking about just the occupancies, not about the names. So basically, effectively symmetrization or anti-symmetrization is done. And basically, I'm specifying these numbers. So I'm saying 1 and 2 is equal to 0 and 3 is equal to 2. I don't know. And 27 is 1. I don't know. Yeah, and I need to specify all those numbers. Okay, so now I am just changing the game. But from this information, I will be able to extract something, and we will see it later, that if I give you this, you will be able to say the wave functions. I am owing you to make this, but the main point which we will see in a moment is that if I will give you all those numbers, you will be able to say the wave functions if you want. Okay, so we are not losing everything, we are just changing the bookkeeping, how we keep the information stored. Okay? You see it? Alex, do you see it? How do you like it, by the way? Will you come with such idea? No, it was just a joke. Whether okay, but this, do you see this game changer? What we are doing here? Danny, do you see it? Guys, also you? I unfortunately don't know your names, so particle number 2, do you see it? Okay, so we are just doing that, okay? So we just changed the information. And now comes this idea what Fogg has, that Fogg define his Fogg space, F. It's a Fogg space. And this is the infinitely dimensional vector space. Okay? And this is the infinite dimensional vector space, and I just know how to call it. So in some mathematical literature, it's given like that, that you take the n omega such that all NE is non-negative numbers, so it can be 0 or positive numbers, but if they are integer, they are positive integer numbers. It cannot be 2.5. Okay, these numbers are 0, 1, 2, 3, 4, 25, any integer number, positive integer number. Okay, so you make such things, and integer, so these they are integer. And you make something like the linear space of that. So did you hear in the algebra something like a linear hull? The symbol for that is a linear hull. I will explain it. But you know, this space is an infinite dimensional vector space, so it's difficult to given the definition. But it's understand that you are making something what is called a linear span. Linear hull, it's sometimes called hull, or linear span. This is the other name for that. But you will see what I mean. No? You didn't have that? Okay, no problem. You will see it. Okay. So in principle, what I am defining the big list. So this you can imagine as a big list. It's a big list, in principle infinite, or finite. This depends on the system which we are investigating. And you are specifying this list that you are saying the elements of this list. Like if you are doing the programming, so you are saying 1, 0, 1, 3, 0, 0, 5, 0, 0, 20. Okay, this is one element of this space. Okay? And you are able to change all possible numbers how you can imagine. Okay? Is that clear? Great. So it's something very huge. I can imagine it like something very, very huge. Okay, this is very, very huge. Donald Trump would say it's huge. Okay, and then you are basically describing the states, something like that. That you are having a very special state where all the things are 0. And then you would have a states such that on one place there is somewhere 1, but all others are 0. Then you can pick up all the states such that there are states like this. So the sum, if I'm making sum over all n a is going from 1 to omega, then here it's equal to 1. Here if I'm making the summation over a going from 1 to omega, and I'm summing all of those guys, then I'm getting 2, etc. I can chop it, something like that, that here will be the states, such that if I'm summing all those n a is going from 1 to omega, then I'm getting n and things like that. These are called sectors. So this is the 0 particle sector of the Fogg space. This is the 1 particle sector of the Fogg space. This is the 2 particle sector of the Fogg space. This is the n particle sector of the Fogg space. And in principle, you can go to infinity. So adding particle means just that you are going from here to here. Okay, so you are taking all the possible configuration of the system, n plus 1, n plus 27, infinite, how many you want, okay? So all the things we take together now, okay? So there is not issue of adding particle in principle. All particles are there, okay? Good. This is just the visualization. And now I need to tell you, because it's a vector space, so I need to tell you vectors, how they look like and how we are adding them, okay? So this is just the basis of that vector space. This I want to say is that these vectors which I define, it's not the space at all, it's just the basis of the vector space. So this is like the basis of the vector space. If I have a basis, then I can start to put some coefficient and start to define the linear combinations, and I am creating a vector space. Okay? Is that clear? Good. So these brackets means that I just want to say that's a linear span or linear hull, which means it's a basis of some abstract vector space. Good. So let me write some vector of that. And you will see it's pretty easy. Okay, so if I now take a vector of this vector space, what does it mean? This means that psi, okay, I can call it like that, or I can call it without that bracket, doesn't matter. This really means that I'm taking the linear combination of such guys. Okay, so I'm going from n1 to n omega in principle. Right, here I'm putting some complex numbers. And I'm taking my basis vectors. Okay, I can take apple, oranges, and pears. Okay, so this is apples, and pears, and then cucumbers or bananas. And then I can make a formal vector space out of that. So I will call the vector in my fruit shop is something what has the, I don't know, probability P that it's orange, or I call it apple. So this is the state, plus, I don't know, probability that it is a pear. Okay, plus probability that it's a banana. Okay, so I define the basis, and I'm now making formal linear combination with some numbers. Yeah, and I can say all those states are orthogonal, that apples are orthogonal to pears, and pears are orthogonal to bananas, and bananas are orthogonal to that. Okay, so this is the way what we are doing. So this is the bananas, oranges, occupation numbers, and this is the probabilities linear combinations which we are having, right? Is that clear? Fine, may I go on? Perfect. Okay, so now I need to define the addition. Okay, so if I have the another state, phi, which will be given something very similar. So you see, given a vector phi means I need to give many, many, many complex numbers. Infinitely many complex numbers in principle, right? Okay, so I have now, or I can call them like that. Then I need to know what is the addition, because I said you that it's a vector space. So the question is, how we will define the psi plus lambda phi, the linear combination of those things. And you are intelligent guys, so you say, okay, it's pretty easy. We just add these complex numbers. Yeah, so we take this. Okay, and this thing is not changing. This is the basis. Okay? Clear? We are adding the components of that, right? Super. So I just want to tell you that it's not true this, yeah? If you take the state 0, 0, 0, and then you take the other state, just want to say you that this is not this. We are not adding a basis, okay? You cannot add these bases. This is nonsense. Yeah, you can just add these numbers, and okay, you cannot express that anything better. It's already expressed like that. You cannot simplify it. So this is not allowed, okay? So this is bullshit. You cannot do that. Is it clear? It's like that you are you are adding apples and pears and you say, okay, it's, I don't know, some other fruit. Nonsense, okay? Great. And we just need to define the other things, and we define the inner product. Let me just define the inner product, and then we can make a break. Okay, so inner product, or scalar product I can call it. Or scalar product. And we just say the scalar product is like that. We say that the state n1 till n omega, scalar product with state m1, n omega. I just need to prescribe this matrix. I just need to say what is it, because I'm defining that I have a basis, so I need to define what is the scalar product of that guy with that guy. It's up to me to define it, right? So I will say it's very easy. So if n1 is the same as m1 and n2 is the same as m2 and n omega is the same as n omega, then it's 1. Otherwise, they are orthogonal to each other. Yeah, so the states which different occupation numbers are mutually orthogonal. So I made the definition. So this is the definition. I define it like that, okay? So you can visualize it like that. So if I am writing all my states, I don't know, states alpha 1, alpha 2, alpha omega, and then I have 1 particle, 2 particles, 0 particles, I don't know, 1 particle, and I take another state. We just know that this means just this, and there is a 0 particle, and there are 2 particles, and there is 1 particle, and there is a 1 particle, and there is 1 particle. Those states are orthogonal because, for example, there is a 1 particle in this state, but there is nothing. Of course, this is non-zero, but altogether it's 0. Yeah? States with different occupancy are orthogonal. So by this definition, I said that states with different occupancies are orthogonal. And by this definition, I said that each state, each basis vector is, its magnitude in this big space is 1. So I define the magnitude, okay? So last thing, if I want to define the scalar product of 2 vectors, so just let me write it before breakfast. Oh, breakfast, yeah, before breakfast. So Danny brought me breakfast, so I will have a breakfast today, if you didn't finish. Okay, so the scalar product of 2 general vectors would be understood as a normal way as we know it. So if I have now those 2 guys, right, and I am asking what is their scalar product, let me change it to m1 now because it would be easier. So if I'm now making the scalar product of those 2 guys, let's say the scalar product of the state psi and state phi, then I'm doing it very simple. So I'm making summation over n1 to n omega, m1 to m omega. I'm taking these complex numbers, I am starting them, and I need to make the scalar products of those guys. Okay, so this is just zeros or ones, so I'm getting the very long sausage with some numbers. And this is the complex numbers, so in principle it will be the complex numbers. And you clearly see that if you change it, it has all the properties of the scalar product. Yeah, it's bilinear, it's symmetric or Hermitian and things like that, because I made the definition like this. Okay? So this is the Fock space, abstract space. We are still doing things abstractly. Okay? So let's meet at 9 o'clock and 10 minutes and we continue. Okay? Great. Questions? I will then describe what to do with fermions. Okay. Yeah, for fermions, the numbers can be only 0 and 1. Because we want to put the Pauli exclusion principles. So this is the abstract vector space for distinguishable particles. And also for bosons. But for Fock space, for fermions would be that we just need the zeros and ones because we want to keep the Pauli principles into the game. So the basis would be different. Also, we can see it like that the Fock space for fermions. Do you understand the question what was said and what I'm explaining? Yeah, fermions, you cannot put two states to the same quantum number. So the maximum n is 1 and minimum n is 0. So we are just getting like the list of zeros and ones. Okay? Which we can also imagine that either we define the special Fock space for the fermions, when my basis would be zeros and ones, or we can see it as a special subspace of this generic space, which is just something like, okay, this is the full F, and somewhere here is just some subspace for fermions, which is just composed of zeros and ones. Okay? Just that, yeah. Okay, now you have break. So let's meet 9:10 or 9:12. Okay, simply we will meet here. Huh?